Okay, kids, so today is a continuation of this concept of activation energy, which I know you all graphed on the lab that you handed in with the iodine lab, but we need to talk more about it because it's one of the most important things. So what I've got drawn on this graph shows the number of collisions over here on the y-axis that are taking place at a certain amount of collision energy. So when particles collide, it's kind of like ping pong balls that are bouncing around, or second graders named Timmy. Let's go with second graders named Timmy. Yeah, we'll go with Timmy. And so what the collision energy and the number of collisions are telling you is that how many collisions are in this graph, how many collisions are taking place with a certain amount of energy. So for a reaction to take place, there's what's called an activation energy. So if the collisions don't have that threshold of energy, then they're going to collide, but the reaction isn't going to take place. So what you've got here is that you're going to come in here and say, okay, so here we are at this lower temperature of 70 degrees, which is this upper curve up here. So at 70 degrees, you have a lot of collisions taking place at this value of 10, okay? Typically, this is like joules. And we're just going to look at the shape of the graph. Don't get hung up on what units this is in. This is more of a conceptual idea. So at 70 degrees, you have a lot of collisions taking place at this value of 10. And you've got a small number of them that are taking place over here, okay, that are above that activation energy. Now, if you raise the temperature to 90 degrees, then you get a much broader distribution of where these energies are taking place. And here's what's going to be important. At 90 degrees, you have more and more and more of these collisions that are taking place above that activation energy. So the reaction is going to take place faster. So that's why when you look at that iodine lab that you all just did, when I ran that reaction at like 35 degrees Celsius, that reaction took place very, very quickly because you had so many more collisions that were above that activation energy. When I ran it at that colder temperature, the reaction took forever because of the fact that you had so few collisions that were above that activation energy. So that's the cool thing about, seeing this take place, is that you can kind of visualize this. So the other way that you can look at activation energy is if you go back to this second grader's analogy and you say, okay, here's a pole that the kids have to run up and jump over. So the activation energy is telling you, okay, if you're going to jump over this bar, how many kids are going to have enough energy to jump over that? So if it's really, really, really cold outside, the kids aren't going to be as willing to jump over that bar and clear it, so you won't have as many kids jumping over it. Now, if it's 85 degrees, it's the first warm day, they're out of quarantine at the house, they're going, wow, we've got all this energy. So then you're going to have a lot more kids that are going to be able to jump over that. So here's what's important. When you raise the temperature of a solution, it does not change the activation energy. That's a set value, unless you catalyze it, which we'll get into later. But that activation energy is a set thing, okay? So once that's set, when you raise the temperature, you're just having more and more of these collisions that are taking place above that threshold. Now, here's the other way that you can look at this. So here's another graph, okay? So we got this, we got this. This is energy, and this is the direction of the reaction, and we're going to start here, and we're going to get this going, okay? And here we are with the reactants, and here we are with the products, and this hump right here, kind of like a roller coaster, is your activation energy. So couple of things is going to happen up here. So we're going to look at this reaction of simply some A turning into C. Okay? That's it. So here's the deal. So when you look at this taking place, so here's A, here's C. So what's going to happen is that this energy has to be provided by the collision. Okay, so this is when these things collide. That's what's going to be provided by that collision. So obviously, if the particles are so low that if the collisions have such low energy that they are not able to clear that, then no reaction is going to take place. So here's what's going to happen. You can think of this as being like a roller coaster. So here you are on the reactant side, and you're starting here, and you're going to go up, 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 and then you're going to go woo, and you're going to end up way down here. Now, in this situation, if your products end up with less energy than what you started, and this is going to play into thermodynamics later, but this is going to be an exothermic reaction, meaning that that energy is given off. Okay, oh, put an extra C on there. Don't need that. This is going to be an exothermic reaction. Energy is going to be given off. So what that means is that you can think of this as being like a roller coaster again. Here you are, you're up at the top of the roller coaster, you go, woo, and people scream and they yell, okay? And then they end up here at the bottom of the roller coaster. So you end up down here with less energy than what you started. So this means you're going to have what we call a negative delta E. You're going to end up with less energy. So let's say that we're just going to call this, I don't know, an energy level of 10, and we're going to call this an energy level of 4. So if I take 4 minus 10, I get negative 6. So that means that this reaction is going to lose energy. So now what can also happen, I'll draw this in a different color, and this happens less often, and we'll see why later on once we get into thermodynamics. You could end up at a higher energy state. Now this would be an endothermic reaction. On an endothermic reaction, then the products actually end up with more energy than what you started with as the reactants. This doesn't happen as often. Most of the time, you're going to get an exothermic reaction. Energy is going to be given off, and you're going to have a negative delta E. So when you look at what's going to affect the rate, what's going to affect the rate is, number one, the temperature, okay? And also that's going to affect the rate is the size of this activation energy. So if your activation energy is really, really big, that means it's going to take a lot of energy to get over the hump. If you have a smaller activation energy, then if you go back to this graph, if you can lower that activation energy like back to here, then if you can shift that activation energy back, then you're going to have more and more and more of those collisions that are above that point. So that's basically what you can manipulate. You can manipulate the temperature and the number of collisions relative to the activation energy, or you can shift the activation energy line itself. Now, here's an interesting thing. So typically, when I do this, if I was actually in school, I'd take a hydrogen balloon, okay, and you've all seen this, and I would blow it up. So what happens is that the hydrogen and the oxygen collide, and we end up with water, and it's a very exothermic reaction. So what this state up here is called a transition state. So what happens in this transition state, this is where the hydrogen and the oxygen have broken the bonds, because if you think about it, this is what has to happen. So imagine that you've got like a model, that stick and ball model of a water molecule, and you have some hydrogens over here, okay? Some hydrogen molecules. And you have some oxygen molecules. So if you were to actually build a water molecule, you would have to break the bonds that hold the oxygens together and break the bonds that hold the hydrogens together. And then you're going to recombine them over here, and you're going to end up with water. You all seen this, it's very exothermic. you feel the heat being given off, you end up with a much lower energy state. Now, here's the other thing that's going to happen. If you take water, okay, and you want to break it up and you reverse this process and you want to end up with hydrogen and oxygen, and you all have done this, okay, you've all seen this lab. You did this when you dropped like the battery. When we had the battery, we did the electrolysis section, and you started with water and you had to dump energy in to break them back up into hydrogen and oxygen because it's not going to do this on its own. So if a reaction is exothermic in one direction, if you reverse it, then it becomes endothermic in the reverse reaction. So if you start with water and you want to end up in hydrogen and oxygen, you've got to push this thing way up this hill and then end up over here. Okay, so just kind of a visual in terms of how this deal plays out. So in terms of like an actual reaction, so let's say that we're going to have this molecular compound, and we're going to break it up into hold on, that was a horrible Br2. Okay, so we've got BrNO, and we're going to have a decomposition reaction into 2 nitrogen monoxides and elemental bromine. So on a graph, you're going to start like this, and here's your energy, and here's the reaction. It's going in this direction. So if you had something like this and you were to ask to label the parts, you'd say, okay, well, here's my reactants, NO, Br. Here are my products, NO and Br2. And so since I end up at a lower energy state, I'm going to have a negative delta E, so that means that this thing is exothermic reaction. I've got my transition states up here. So in my transition state, this is where I've broken the bonds that hold the bromine, the nitrogen, and the oxygen together. So I'm going to break those, and then I'm going to end up down here with these products. It's exothermic. I end up with less energy than what I started. So I've got a transition state. Here's my products. Here's my reactants. Hey, we're off to the races. Now, sometimes you can get, and this is where this becomes a little bit more complicated. So if you remember, you can have like where you have like complex things, where you have reactions that form a product, and then that product gets consumed. So here's how we handle that. So here's your energy, here's the reaction, okay? So you can also have, it's kind of like a camel. So you're going to have 2 different activation energies, an activation energy here and an activation energy here. So in this situation, let's say that we're going to take A and we're going to turn it into C. But within this, we know that we're going to form, somewhere within this complex, A is going to actually turn into B, and then B is going to turn into C. And so like this might be, this B into C is going to be my fast step. Now, when I look at this graph, this is how I know this is going to be the fast step. So here's A. I've got a transition state up here. Here's going to be B. Now, B is at the bottom of this. This is my intermediate. So I'm going to form B right here, okay? But because B turning into C is my fast step, it doesn't last very long. So this is where this idea of activation energy fits with this. So this has a much lower activation energy than the first step does. So that means that this reaction is going to take place very, very quickly. So at that particular temperature, because it has a low activation energy, that means a lot of these reactions are going to be above that activation energy threshold, and the reaction is going to take place very quickly. So I'd have a transition where I take A, something's going to happen here. I'm going to form an intermediary of B, which is what I've got here. And then B is going to have a second transition state up there at the top. And then C is going to end up down here. So overall for this reaction, I know that it's an exothermic reaction. Okay. I've got a slow step because I've got a big activation energy. I'm going to form B. There's my intermediary. I'm going to have another transition state, and then I'm going to end up with C with an overall exothermic reaction. So here's the other thing to look at, is that when you lower that activation energy, assuming your temperature stays constant, the reaction is going to take place faster. Okay, now let's talk about a catalyst. So on your cars, you all have a catalytic converter. So what a catalyst does is that a catalyst lowers the activation energy. So let's say that this is your normal graph, okay? Here's your reaction. So you start like this, okay? So this would be like your normal reaction. Here's my negative delta E. Life is good, okay? Now, if you have a catalyzed reaction, what the catalyzed reaction does is that it lowers your activation energy. So with lower activation energy, the reaction is going to take place faster. Now, here's what's important about catalyzed reactions. Notice that it does not change my overall delta E, okay? It doesn't change delta E. All the catalyzed reaction does is that it lowers the activation energy, provides a new pathway. So that's going to be huge. So one of the things that, like for example, if you look at potential fuel sources beyond carbon-based fuel, is building hydrogen fuel cells where you take hydrogen and it reacts with oxygen and you get water, okay? But you have to store the hydrogen. Well, the question is, where do you get the hydrogen? Everybody says, well, let's take water and we'll provide electricity and we'll break it up into hydrogen and oxygen. Okay, that's cool. Where are you going to get the electricity from? Oh, well, we'll use solar, we'll use wind, we'll use whatever. Okay, you have to have a source of energy. So one of the things that they're working on is if you start with water and you break it up into hydrogen and oxygen, so in other words, you push this thing back up the hill, one of the things that they're looking at is the catalyzed reaction to reduce the energy input to separate water back into hydrogen and oxygen. So even on the reverse is true. So if you can have a catalyzed reaction on the decomposition of water into hydrogen and oxygen, so if you can catalyze that reaction and lower that activation energy, then that's going to take a lot less energy input to take water and separate that into hydrogen and oxygen. Okay, so now these equations that I'm going to give you, okay, are not on your equation sheet, but they're important in terms of how this deal is going to play out. So we've already talked about one of them. You all have done this. Natural log of K equals negative E sub A over R times 1 over temperature in Kelvin plus the natural log of A, okay? And this is Y equals mx plus B. Here's your y-intercept. This is on your y-axis. Excuse me, this is on your x-axis, okay? So you all have done this graph, 1 over temperature in Kelvin. You took the natural log of your reaction rate constants, okay? And remember, you do this graph and you get something like this, and you can find that slope, and then that slope, excuse me, equals negative E sub A over R. You all have done this calculation. You multiply R by the slope, boom, you get your activation energy. Now, This is a cool thing mainly because of the fact that this we can't, like, we don't have activation energy probes that we can plug into the LabQuest. This is about the only way that we can figure out what these activation energies are. Now, if you work backwards from this reaction, and this is one that if you need this on the test, I will give this to you, okay? So here's your rate constant again. And this A is what's called the frequency factor, which is the same A that's up here. And that tells you the number of collisions that are favorable for the reaction to take place. And this is your temperature in Kelvin. And this is your activation energy. Now, everything here, that activation energy has to be in joules. Your R has to be in joules per mole Kelvin. And that temperature obviously has to be in Kelvin. So these two basically are kind of two sides of the same coin. So you got this equation, and again, if you need these on the test or on the assignment, I will give these to you. So what you're typically going to do out of this reaction is that with this one especially, what you can do is figuring out what's going to happen when you compare two different temperatures. So, and I'll get back to the second one in just a second. So how this is written is that if you want to compare reactions at two different temperatures, you can take the natural log of K1 over K2, E sub A over R, 1 over T2 minus 1 over T1. So basically all this is doing, and it looks horribly, horribly complicated, but it isn't. So here's your natural log of K. Here's 1 over temperature in Kelvin. So all this is doing is that, let's say, for example, this is just a jacked up, really jacked up slope-intercept form. So what we're saying here is that here's this temperatures, okay? So if you know a couple of these temperatures and you want to find out what that new K value is, all these are a series of K1, K2, and temperatures. So all this equation allows you to do is, if you know 3 of the 4, you can figure out what the other one is going to be. So that's it. So don't flip out and go, oh my God, this looks like something new. It's really not, okay? So what's going to happen on the assignment, and I'm going to send you the answer key to this. And if you need this, like I said, do not memorize this equation. If you need this on the test, I will give you this equation. So all this is telling you is saying, oh, okay, right. If you know 2 of the temperatures and 1 of the Ks, you can find the other one. Or if you know 2 K values and a temperature, you can find out what the other temperature is going to be. That's all this is trying to do. Now, here's the last kind of big equation out of this. And that's F equals E fraction of that have an energy above the activation energy. Okay, so here's what this, and again, do not memorize this equation. All this is telling you is that at a certain temperature, what it's going to tell you is what collisions are above a certain threshold. Okay, that's all that's telling you. So let me work through some examples. So let's say that, and I've already done the math on this, so let's say that our activation energy is negative 1,000 joules per mole. Okay, there's my activation energy, just to make the math easy. R is going to be 8.314 joules per mole Kelvin. And let's say that we're going to run this at, 293 Kelvin, which would be about 20 degrees Celsius, which is kind of room temperature, okay? Now, if you run these numbers, trust me on this one, you're going to get 0.663. So what that means is that at this temperature, 0.663 or 66.3% of the collisions are going to be above that threshold. Now, let's play the what if game. If we do the same thing, but the activation energy is negative 2,000, in other words, so now this activation energy has gone up, and everything else stays the same, 8.314, we're still running at 293 Kelvin. Now that frequency factor, or that fraction, is going to be 0.44. So by raising that activation energy, even though the temperature stays the same, we have a smaller fraction of those collisions that are above that activation energy. Guess what? The reaction's going to slow down. Now, if you go back to this first one, and let's play the what if game again. Let's say we still had that same activation energy. We still had the same R, joules per mole Kelvin. And now, let's say that we've dropped that temperature to 203 Kelvin. Okay? Hold on. Now, we went from 293 Kelvin to 203 Kelvin. So, comparing these, here's what's going to be important here, kids. Pay attention. Comparing these, we kept the activation energy the same, but we've dropped the temperature. Now, look what happens to this fraction. Wait for it. It's going to go down. So now, instead of having like 66.3% of the collisions that are above the activation energy, now we only have 53.3% of the collisions that are above the activation energy. Guess what, kids? The reaction is going to be taking place slower. So, that was a brutal long lecture. So, here's the deal. I'm going to give you the assignment, and I'm going to send that answer key out with it. Make sure that you know what you got going on. Today, I'm going to sneak over. Well, maybe. No, I'm not. Well, yeah, I am. It's a bold-faced lie. So I'm going to sneak into the school, and I'm going to run the next lab. I will get that lab out to you tomorrow. And with that data, actually, if I get it all done, I might get it out today. So anyway, I'll get this sent out to you. Good luck. Stay safe, and we will talk